Friends, as a part of e-learning process of the subject computer intelligent manufacturing, today we are going to discuss an important topic, that is flexible manufacturing systems. In the previous lectures, we have covered group technology, CNC machines, computer-aided process planning, and several other things. And what is the role of the CNC machines and other automation processes that are to be adopted on the real shop floor is the subject of discussion today. That is, the manufacturing systems at the shop floor today has to meet the demand of mid-volume, mid-variety production system. We have seen that mass production systems, job shop production systems, where in job shop the variety is more and the number of jobs are less. Jobs are more, whereas in the job shop system, the product variety is more and the product volume is less. On the other hand, in a mass production system, the product variety is less and the product volume is very high. But the demand of the market today is that we need a manufacturing system which can address or which can meet the demand of good variety of parts with good volume of parts. It is nothing but a flexible manufacturing system wherein we can use a lot of CNC machines and other things. We are going to discuss in another 1 hour on this topic. The outline of the course is the introduction, elements of FMS, the layout of FMS, processing stations and other, material handling systems, tool management controllers, and design of FMS. The origin of some FMS, if you consider, it is because of numerical control machines and the automated conveyor systems maybe resulted into today's FMS because NC or CNC machines are important components. The transfer of work to pieces and work parts between the machines is by automatic conveyor. And the FMS is almost, because it is a mid-volume production system, it is can consider as a batch processing system. Let us just discuss the brief history of flexible manufacturing systems. Flexible manufacturing systems first proposed in England in 1960s. System 24 was operated. System 24 was developed at the time, which has been operated for 24 hours continuously. Automation is the main purpose for the development of this FMS. We have manually operated machines since 1700s, and later Roger Woodbury made the milling machine, steam and electrical powered machines since the 1820s. Then 1940 onwards the CNC machines, and 1960s onwards, particularly from the year 1962 onwards, the computer numerical controls being used industrially. Manufacturing systems awareness since Henry Ford time, that is from 1910 onwards. Numerical control of machine tools, its R&D efforts and development at MIT during 1950s. From the Second World War, the gun servos, and early 50s, the important SAGE project, the computer-aided design at MIT in the 1960s. The main emphasis is that if the computer can guide the tool, then it can hold part shape in its memory. So let us just discuss partly the numerical control technology. Initially, one computer is used to control one machine. Later on, the development of automatically programmed tool made application of one computer to control several machines. And the concept of distributed or direct numerical control has come in 1970s. By 1980s, each machine had its own computer, possibly loaded with instructions from central computer CNC machines. And on the other hand, we have automation like fixed automation, automated processes like automated material transfers like in mass production systems, automated assembly systems, automated assemblies, processes linked by automated material transfer, and then they all developed into flexible manufacturing. Group of processes arranged in sequence, connected by automated material transfer and integrated by a computer system is a typical FMS. I've been telling you that mid-volume, mid-variety production system. FMS is a mid-volume, mid-variety production system. This figure indicates that in a continuous production system, you take, this is high volume, low variety processes. It is a continuously producing same parts, maybe several hundreds per hour. Its average production per annum would be more than 10,000 pieces. On the other hand, you see the variety is very high. See in this, one or very few unit per lot. Call that as low volume, high variety processes. Very high variation costs are resulted into that. And we get the flexibility is very high, the volume is very less, the production volume is less. And if you see that, if you categorize this volume versus flexibility or flexibility versus volume, we have the continuous systems where the volume is very high, production volume is very high, production flexibility is less. On the other hand, we have very low volume and high variety production system. This is also a graph, another graph. You can see that process design depends on product diversity and batch size. Number of product designs, if you take it on x-axis, and batch size is on y-axis, processes are focused and job shop. You have, because of the processes, variety of processes to be imported, and the jobs, variety of products can be manufactured, and the batch size would be invariably very less. On the other hand, product focus dedicated systems, we take the extreme one, where batch sizes would be high and the number of product designs are less. And in between, the cellular manufacturing product focused batch systems, they occupy this. Now, you see how the flexible manufacturing systems occupies the place in between the variety and volume with respect to products being manufactured. And a dedicated automation we have, you can see that more than 10,000 to lakhs, several lakhs of components can be produced per annum, whereas the product variety is very less, maybe one or two or few variety. Whereas on the other hand, general purpose machines, that side, we have variety of products, maybe 1,000 or 100 like that, and the volume is maybe around 1 to 10 like that. And we have an FMS which is occupying in between. And different other production systems, you can like focused automation and computer integrated manufacturing, the object of the course will occupy the certain to certain other extent also. We are going to discuss about those things later. So flexible manufacturing system, that's why called as the mid volume and mid variety production system. That means in an FMS, we can produce variety of parts, maybe around 10 to 100, and production rate of these parts may be around 100,000 per annum, like that. We have very much successful FMS installations all over the world. Cincinnati Blackram in US, Xerox company in US, there are several examples of successful FMS installations. Now, coming to the definition of this, let us see the developments and the definitions of an FMS. Early FMS were large and very complex, consisting of dozens of CNCs and sophisticated material handling systems. They were very automated, very expensive, and controlled by incredibly complex software. There were only limited number of industries that could afford investing in a traditional FMS as described above. Currently, the trend of FMS is towards small units, small versions of traditional FMS or flexible manufacturing cell, wherein cells, the number of CNC machines are less in number. Only 2 to more CNC machines are considered as an FMC, or flexible cell, and 2 more cells are considered as FMS. Few flexible manufacturing cells will form a system. Thus, a flexible manufacturing system consists of several machine tools along with tool handling devices such as robots, arranged so that it can handle any family of parts for which it has been designed and developed. A flexible manufacturing cell consists of 2 or more CNC machines, a cell computer, and a robot. A robot is the primary material handling device, wherein it will take the work parts and load it onto the machines, and finished work parts from the machines and load it onto the bins. It does that. And a cell computer, today you can say that any other PC, Pentium PCs, they can typically, there may be a programmable logic controllers or interface with microprocessors of robots and CNC machines, and all of them will be controlled by the so-called cell computer. You see the certain layouts of this cellular manufacturing or flexible manufacturing lines. We have a U-shaped systems here where the machines, 5 machines are placed, and at one place work pieces are loaded, and the same place the work pieces are unloaded. The work parts are automatically transferred from one machine to the other machines in a sequence. In your line layout, you see that the work part is loaded at one end and the finished part is unloaded at the other end. The machines or the processing stations are kept side by side all along the line. When the work part transfers from one machine to the other machine, okay, and when it stops, automatically the machining takes place. So here the work part will transfer for some time and stops for some time. So a conveyor belt with intermittent stoppages can be used as a material handling or material transfer device. In another layout, you can see that this is called as a looped layout. Machines are kept side and opposite side, like a conveyor is kept as a loop, and the work parts will be moved on the conveyors and the machines are placed along the conveyor. And the loading and unloading can be done at the same place. I would like to tell you the importance of the cell controller. The functions of the cell controller include workload balancing, part scheduling, and material flow control. The supervision and coordination among the various operations in a manufacturing cell is also performed by a cell computer. The software includes features permitting the handling of machine breakdown, tool breakage, and other special situations. Sometimes in a flexible manufacturing cell, a robot is used. Such a robot is called as a cell robot. The functions of the cell robot are: the cell robot can also perform tool changing, housekeeping functions such as chip removal, staging of tools in the tool changer, and inspection of tools for breakage or excessive wear. When necessary, the robot can also initiate emergency procedures such as system shutdown, etc. A flexible manufacturing system is a set of numerically controlled machine tools and supporting workstations connected by an automated material handling system and controlled by a central computer. The capability of producing different parts without major rerouting, a measure of how fast the company converts its processes from making an old line of product to produce a new product. The ability to change a production schedule to modify a part to handle multiple parts. These are all called as different flexibilities. An FMS is a reprogrammable manufacturing system capable of producing a variety of products automatically. Conventional manufacturing systems Conventional manufacturing systems have been marked by one or two distinguished features: the capability of producing a variety of different product types but at a highest cost, the capability of producing large volume of a product at lower cost but very inflexible in terms of product types which can be produced like in transfer lines. An FMS is designed to provide both these features. Need to use FMS to reduce setup and queue times, improve the efficiency, reduce time for product completion, utilize human workers better, utilize machines better, improve product routing, produce a variety of items under one roof, improve product quality, serve a variety of vendors simultaneously, produce more products quickly. The features of FMS are: many part types can be loaded. Parts can arrive at machines in any sequence. Parts identified by part codes or barcodes which are available on the parts. Many machines can be included. Small FMS lead to flexible cells. We already discussed that. Expensive to implement, but savings can be significant because of initial investment. Because of automated material transfer, all CNC machines or automated workstations, FMS installation cost is very high. However, the return investment is very high. You can get back the investment maybe within 5 to 10 years of time. Expensive to implement, but savings can be significant. Reduced direct labor costs, 3 shifts continuously feasible, and it is ideal for just-in-time system. You can also utilize the floor space efficiently. Equipment utilization is up to 85%. Detailed production sequence not needed well in advance. Reduced variable costs and throughput time lead to enhanced manufacturing competitiveness. Elimination of startup cycles lead to standardized performance. And a modular design concept we can implement, and it can be easily turned over to a new set of products if the need arises because of the product variety is high. Because if the company requires to meet the due dates. If the company requires the utilization to be maximum, because the kind of machines that are using are high in cost, and they wanted to have the throughput time, minimum throughput time, and wanted to maintain minimum work in process levels, one need to go for the successful installation of flexible manufacturing systems. Each FMS is designed for a specific application, that is a specific family of parts and processes. We have discussed in the last group technology class that the parts can be classified into part family, and simultaneously the machines that are going to process these parts, okay, we call them as machine family. So by group technology methods, applying the GT methods, we can simultaneously formulate machine families and part families. Put 2-3 families together and put 3 to 4 families of machine families together, and then these machine families, if you arrange them with an automated material handling system, right, and this set of part families, we can call them as a system, and it is now capable of producing those 3 to 4 variety of part families. So part variety has been enhanced and production is not disturbed, and it can be classified accordingly: kinds of operations, processing operations, assembly operations, number of machines, which can be a single cell or 2 to 3 machine flexible cell, or several machines flexible manufacturing system. Another classification of FMS is according to the level of flexibility designed into the system. This method of classification can be applied to systems with any number of workstations, but its application seems most common with FMCs and FMS. Two categories are distinguished here are dedicated FMS, random order FMS. We have an FMS here with 2 machines, 1 host computer and 1 robot. Let us now discuss the FMS layout. I gave you the brief sketch of the layout in the initial stage of this lecture. As inline FMS layout, FMS loop layout, FMS ladder layout, open field FMS layout. Progressive layout, all parts in the production process follow the same progression through the machining station, best for producing a variety of parts. Closed loop layouts, arranged for the general order of processing for a large variety of parts. Parts can skip stations for flexibility, used for large part sizes, best for long process times. This is inline FMS layout, where the loading at one end and completion of the parts at the other end. Work parts are flowing from one end to the other end and getting processed on the various CNC machines or automatic machine. This is inline. This is also a linear kind of transferring of parts, but here a secondary material handling device is used. Like the parts are transferred from the primary material handling device, like a conveyor, to the machine by a secondary material handling device. It can be a robot or it can be a automatic material transfer device, and the same device will unload the parts from the machine to the conveyor. So secondary material handling device function is to transfer the material or transfer the parts from the primary material handling device like conveyor to the machine, and from the machine to the conveyor. This is the secondary function, secondary handling device function. And we have here both primary handling devices and secondary material handling devices. So this is another type of layout, and you can see this is a FMS loop layout, where the layout is is like a loop fashion. The machines are arranged along the conveyor belt with secondary material handling devices. And the figure is self-explanatory, where you can see the part transfer and secondary handling system, how it transfers the parts among the various machines. This is a rectangular layout for recirculation of pallets to the first workstation in the sequence. This is used. The recirculation of pallets is necessary for sometimes, because the machine is used for more than one process. In that case, suppose the process 1 is done on machine 1 and again process 20 is to be done on the same machine. Then the part has to revisit the same machine. So this is called as recirculation of parts, and the system should be capable of allowing it. This can be done in this kind of loop layout, a rectangular layout with the recirculation of pallet. And the pallet is moving, it can move for the 20th operation to the same machine. Like this is another kind of layout which is used for recirculation. This is an FMS ladder type layout where the several loops exist within the layout, and the material transfers asynchronously in this. Asynchronous means not necessarily in a sequential manner, not from one machine to the other machine, and it can move. The parts can be moved either to machine 1 or machine 5 or machine any machine at any time. Normally, material handling devices that are used in this kind of layout are AGVs. AGVs are best to use as material handling devices in this. Since AGV is used as primary material handling device, we must have to use robot as a secondary material handling device. Robots will pick the parts from AGVs and place it on the machines. And AGVs can move asynchronously in this layout, but other problems like traffic congestion and collision, several problems may arise, and those have to be addressed separately. And this is one layout where a lot of advantages exist. Highly flexible layout. Open field FMS layout. This is a typical FMS layout being implemented in many practical situations where it has a loop layout with ladder structures, and you can see that if you have a very big system with AGVs moving around the machines, and the AGVs docking stations are also available here, and part cleaning stations and other stations can be available in this kind of layout. You see this figure. In this, a single machine is only used, so we call it as a flexible manufacturing cell. Only single machine or a machining center is used, which is capable of producing capable of doing more number of operations, and a single machine cell looks like this. And here also the pallets are transferred. Pallets along with the workpieces, can be transferred from the conveyor belt to the machine, and then from the machine to the conveyor belt through the secondary metal handling device. A shuttle cart, for example, is used here. Another flexible manufacturing cell is in which 3 machines are kept side by side, connected by a conveyor system and shuttle cart. Features of the 3 category of flexible cells and systems. We have seen that in the system many number of machines are used. In the cell, few number of machines are used. In a single cell, only one machine is used. When you have the one number machine, the investment is less. When you have more number of machines, investment is high, flexibility is also high, and production rate is high. When you have more number of machines, both flexibility and production. Flexibility criteria apply to 3 types of manufacturing cells and systems. You can see in this table, a single machine cell, part variety is yes, but processing is sequential, not simultaneous. Schedule change, yes. Error recovery is limited recovery due to only one machine. New part, it is capable of producing new part, yes. Flexible manufacturing cell, part variety, yes. Simultaneous production of different parts is possible. Schedule changes, yes, it accepts. Error recovery is limited by fewer machines than FMS, and new part production is yes possible. Coming to the flexible manufacturing system, yes, simultaneously production of different parts is possible, and schedule changes is possible, and machine redundancy is minimizes effect of machine breakdown, thus production is more, and new part, addressing of the new part or production of new part is very high. Manufacturing flexibility, what is this? Basic is that the machine can produce variety of operations. Material handling, part mobility and placement must be more. Operations wise, variety of operations producing same part features should be more. The system that is required is processes should be wide variety of processes of parts capable of producing within the same setup, Routing, ability to use different machines under the same setup to be more, and product changeover should be good, and volume production level is high, and any capacity expansion should be allowed. Aggregated, it should be, the program is such that it should be run in an unattended fashion. Production of large parts, products, processes, volume and expansion, and the market demand is combination of product, process, volume and expansions. Thus, in an FMS cannot remove variability from the system, but flexibility enables it to perform effectively. Degrees of flexibility of FMS. In the dedicated FMS systems, limited variety of part styles is allowed. Complete universe of parts are known. Machine designed with specific process required to make the limited part family, an increasing production rate and flexible transfer line. A random order FMS. Large part families, substantial variation in part configurations is allowed. New part designs and engineering changes in the parts is highly allowed. Production schedules changeover from day to day is allowed, and the general purpose, like generally it uses like general purpose machines, systems, and more computer programs, more computer control is required. Comparison of dedicated and random order FMS. You can see that flexibility wise, the random order FMS is more, dedicated FMS is less. Production rate wise, dedicated FMS is more compared to random order FMS. This is another table which has shown previously like that, and it is also a self-explanatory. Please read it. And let us now discuss about the important components of an FMS. Tomorrow you wanted to implement an FMS in your factory, or you wanted to convert your conventional production system into flexible manufacturing systems. You must know what are the important components of an FMS. The processing station must be computer numerical control or assembly, automated assembly machines. There must be computer controlled. There must be automatic controls with a control with a PLC based or computer based control. And all the machines must be connected by means of automated material handling systems. Maybe the different kinds of conveyors, automatic conveyors, robots, or AGVs, or sometimes ASRS, automated storage and retrieval systems. They are all used as automated material handling systems in FMS. And we need to have the tool supply systems and computer control software and human labor. There is a role of the human beings to play in an FMS situation. You see this, the flexible manufacturing system. They are all machines being the workpieces being transported from the loading station to this as per the process sequence, and the required CNC programs will be downloaded as per the movement of the parts among these machines. The part programs are downloaded and the machines are routed to those as and when a particular machine, a particular part reaches a machines and placed on the machines with the help of pallets. Pallets are automatically placed with automatic setup dock pins. The pallets will be located on the machine. So as and when a particular part is loaded on a machine, the part will be read, and accordingly that particular program for that part is loaded, and the machine start processing that particular program. This goes on. Once the machine is processing the program, the tool selection and the tool life, how much is the remaining tool life of that particular tool, they're all automatically recorded, and in the automatic tool library that maintains by the controller, all this data is appended. So we'll come to know what is the remaining life of the tool on each machine. Suppose any tool was broken. The tool is broken. We have once the tool is broken, the machine gives a signal to the controller that the machine has under a breakdown stage due to the tool failure, and the human operator is required who can come and change the tool at that time and replace the tool with a new tool or with any other user tool. He has to do it, and he need to do presettings. Like that, the machines works, and the supervisory controller or computer controller will take care of the utilization of the tools and movement of the parts among the machines, everything, and at the end of the processing, we get a finished parts at one end. which can be unloaded. Flexible assembly systems, we have flexible manufacturing systems. Manufacturing includes machining as well as assembly. We have assembly systems wherein several parts will be assembled by the assembly machines. The assembly machines can be automatic assembly machines or robotic assembly machine. A robot can be used as an assembly machine. Two parts put together with temporary joining method like fasteners and other things, or snag fits and other methods, we can join A plus B, two parts. Or there is another method is permanently joining of two parts. Part A can be joined with part B by means of welding and other permanent fixing methods. For the combination of raw materials and components into products with functional characteristics, and we need to use a lot of devices like feeders, hoppers, computer aided vision systems to take care of the assembly. You can see this is a complete simulated model of an FMS, typical FMS. An FMS design and how it looks like has been built up using one of the simulation packages. It looks like this, and we can use simulation, which is as a tool to know the performance of this kind of factory. A factory which you wanted to construct can be simulated in a simulated environment, placing all the machines, placing all your conveyors, robots, etc. Give the processing times for these machines, processing rates and other things, and you can run the simulation model and you get what could be the output and performance measures of this, etc. There are several languages which are available to do these simulated, to create simulated models and test the FMS performance. They're all called as discrete event simulation models. It is another schematic view of an FMS making 600 aircraft components, and we have variety of computer aided inspection stations along with manual inspection stations, AGV maintenance areas and machining centers, pilot changing stations, etc. are available. Cleaning stations and automatic chip disposable or chip removal stations, they are all available in this FMS, which is very big size. Integration of FMS, we can divide that. The equipment can be classified as primary equipment and secondary equipment. Primary equipment includes work centers. What are the work centers? Like universal machining centers, like horizontal machining centers or vertical machining centers. And in certain machining centers, both these two facilities are available, both horizontal as well. And universal machining centers and turning centers, grinding machines, CNC grinding machines, CNC nibbling machines, and processing centers like CNC washing machines, computer numerical control, coordinate measuring machines, CMMs, robotic workstations, and certain manual workstations. Coming to the secondary equipment, we need to have support stations like pallet fixers, loading and unloading stations, tool commissioning and setting stations or area, supporting equipment like robots, pallet fixers, tillage stores, pallet buffer stations, tool stores, tool loading places, raw material stores, transportation of parts by AGVs, RGVs and robots, transport units like pallets and stillages. Machines, you can have the machine that produce prismatic parts or rotational parts, horizontal machining centers and head indexers, tool magazines and automatic tool changes, and part movement is done by conveyors, tow cars, rail cars, AGVs, RGVs, etc. Supporting workstations, load-unload stations, automatic part washers, automatic painting stations, coordinate measuring machines, online inspection devices, material handling systems, automated guided way, automated storage and retrieval systems, robots, conveyors, an FMS controller, invariably a computer, and programmable logic controllers, and human being like a attendant, tracking system for parts, machines with all barcode readers, with all sensor inputs and outputs. Software system structure of FMS application. You can just see through this, go through this program. You go through this slide. It contains numerical control machine. It download a particular program to a particular machine and also send a signal to the transport controller, and that sends a signal to the particular AGV or conveying machine to move the part from the given location to that particular machine. So it has to send several signals for movement of parts, for starting and stopping of programs, and loading and unloading of the programs onto various machines, and also receives the signals from the respective machines that the programs end of the program or breakage of the machine tool, everything. The such kind of things will be compositely done by the compositely done by the so-called cell controller or system controller. Advantages: productivity increase due to automation. Preparation time for new products is shorter due to flexibility. Saved labor cost due to automation. Improved production quality due to automation. However, it is not always necessary that on increasing flexibility, productivity is also increases. There are certain disadvantages with FMS. One is more expensive because of high capital investments. Sophisticated manufacturing system. Maintenance is very complex. Substantial pre-planning is required. Technological problems may arise and we need to have a technologically challenging problems and solution team. Applications: machining all kinds of products, assembly of parts and equipment, sheet metal press walking, metal forming processes, welding industry, semiconductor product manufacturing, textile machinery industries. You can see some real world examples of FMS installations all over the world. The first and foremost example is, I can quote that, is the Ford Motor Company. At Ford Powertrain, they face the following challenges: outdated cell controller, lack of flexibility because of it causing loss of efficiency. Solution proposed: implemented a cell control based on an open architecture, commonly available tools, and industry standard hardware, software, and protocols. Through the use of reprogrammable tooling in the body shop, standardized equipment in the paint shop, and common build sequence in final assembly, Ford can build multiple models on one or more platforms in one plant. You see the body shop, paint shop, and final assembly. The final assembly area has been shown here as a simulated model. This simulated model has been created using Quest software, and the flexibility means the build sequence in the same among the multiple models, one or more platforms, allowing for efficient utilization of people and equipment. FMS example 2. Virtual manufacturing technology allows Ford to quickly add various models into an existing facility. So they have studied the application of or production of variety of models using the same facility by simulation. This is a simulated model, which we call it as vertical manufacturing. Cell or technologies have been used. In the virtual world, manufacturing engineers and plant operators evaluate tooling and product interferences before costly installations are made on the plant floor. This method of collaboration improves launch quality and enables speed of execution. These are all required as a pre-planning activity for implementation of an FMS. You must model the entire FMS in a simulated environment and evaluate that model and study and plan accordingly. You must have to implement. FMS example of Ford again. Design one assembly process. Multiple models can be built up in this way. See here. Challenges with FMS. Determining if FMS is the best production system for your company. Are you willing to accept this? Is FMS the best production system for your company? Possible expansion costs associated with implementation of FMS. Day-by-day maintenance of FMS operations is different. Benefits. Enabled Ford to mix and match from different vendors. Machine tools reduce the number of man years required to implement the application. The budget of the fully automated closed loop controller was less than 1/10 the cost of the system built in long ways. No formal training was required for the shop floor operations. An example of simple and modern manufacturing system. This is another FMS where you have universal machining centers and you have AGV transportation system. AGVs are used to transport the material from the raw material area to that. And you have the host controller. You have also assembly cells. Not only manufacturing of the parts, but also assembling of the parts is done in this. So, like this, there are several FMS installations are available in the world. They are successful. Certain practical situations in Indian scenario, FMS is practically demonstrated in some of the defense organizations where arms are manufactured, like the FMS in gun factory, the FMS installation in Iddu Mailaram. FMS installations are available in India also. And one FMS installation has been designed and fabricated in BHEL R&D cell. Some FMS installations are available in the defense manufacturing units, and one FMS cell is also used in one of the heavy machinery equipment manufacturing plant, Haridwar. And these installations are to be, they have been practically used, and one has to evaluate implementation of this technology, gain the advantage of the technology with respect to its socio-economical condition. With this talk on flexible manufacturing systems is over. Thank you very much.